in the relationship, right? And so if we do the experiment, there are always errors. For example, there are always errors caused by your equipment, and there are errors caused by your observations, right? So you can never get the true value of the parameters, but only their estimate. So that's why it is called parameter estimation. So our goal is to obtain the best estimation. So I'm going to explain what our best estimations are. So simply put, during our research, we propose a true model due to our own understanding in this area, and we specify its parameters, and then we measure x and y in our experiment, and then we use this data to estimate my parameters. And we also need to report error analysis, which means how good this parameter estimation is. But because of the time issue, I won't go through that, but I want you to know that it's also important. Okay. So the next step is least square method. I said we need to do a best estimation. So what are the standards for the best estimation? So first of all, I want to clarify between some variables. So this one, yi, is an observed dependent variable. It's observed value in your experiment. But yi hat is a predicted dependent value, which is calculated by your predicted parameters. Okay, y hat is predicted value, and yi is observed value. So generally, are they different or are they the same? Generally, they are different, right? Because one is from your experiment and one is from your estimation. They are different. So we use this concept named residuals to explain the error between your observation and your estimation. The bigger error, the bigger the residual, the worse your estimation is, right? So here's an important concept, the sum of square of errors. So that means this is a sum of the square of errors. So this is yi minus yi hat squared and sigma. So this is kind of a matter of the overall error. So the question is, the larger SSE, the better or the worse the estimate? The worse, right? Because our overall errors are bigger. So for example, the same model, and this is our observed set of data, and if I use this set of parameters, this is our predicted y value, and this is our residual, and then the sum of square of errors will be 3.25. But if I give you another set of parameters, this, and a new set of predicted values and a new residuals, and the new SSE is 2.5. So this one is less, is smaller than this one, right? So we can say this estimation is better because it gives us less errors.
Excuse me. You said 2.5. I see 2.4 on the screen.
2.4. Yeah, you're right. I'm sorry. Yeah, you're absolutely right. Thank you. Okay, so this one is 2.4. Okay, so this is not important. The key point is that it's smaller. We see that the different parameters will have different SSE. Okay, so the smaller the SSE, the better the estimate. Now, so our goal is to minimize this SSE. When I got the minimum SSE, we got the best estimation. So that's why it's called least square method. That means we need to get the least square of errors. So the minimum of SSE, we choose a set of data to give the least square error, which means the derivative with respect to the parameters is 0. Right? So this is from our calculus, knowledge of calculus. So for example, this is our model, and this is SSE, and we need to do the derivative with respect to the parameters. I need to the derivatives to be 0. Okay, so we have two unknown parameters here, and we have two equations. So we can solve it, right? So after some rearrangement, we got this